We're going to compare two examples when to be used. For example, the cylindrical coordinate system to solve the triple integral, and when do we use the spherical coordinate system to solve the integral. So, and equal to x1. So take a look at this case, this scenario. Here, what do I see? I see z equals to 4 minus x squared minus y squared. If z is equal to 0, I get x squared plus y squared equals to 4, which is the base of a cylinder. Am I right? So, since I have a base of a cylinder in this scenario, in this case, I prefer to use cylindrical coordinate system. So let's write this down here, cylindrical. Now let's take a look at this guy here. I have x squared plus y squared plus z squared, and I also see a solid sphere here, a solid sphere. Since I have a solid sphere here, and I also, this is the base that you have that you're working with, which is a spherical form. So it's easier to convert everything into spherical coordinate. And also take a look at this, x squared plus y squared plus z squared, which is just rho squared. That's how we are using two different types of techniques to compute these integrals. So in cylindrical coordinate system, remember that x was defined as r cosine theta, y was defined as r sine theta, and z was defined as z. Our job is to identify what is theta and what are the boundaries for our r. So take a look at this. First of all, z is equal to 4 minus x squared minus y squared. So x squared plus y squared is equal to 4, or r squared is equal to 4, r becomes 2. It means that my radius is bounded between 0 and 2. What about theta? There is no restriction here. So my theta is bounded between 0 and 2 pi. You can visualize this guy as well. It's not that difficult to graph this paraboloid. It opens downward. So this is my z equals to 4 minus x squared minus y squared. And as you can see, you have a base, and theta ranges between 0 and 2 pi, and r is bounded between 0 and 2. Negative 2 and 2, and this is yours. So what about my z? Can I convert my z into r and theta? Of course. My z is equal to 4 minus x squared minus y squared, which is equal to 4 minus r squared cosine squared theta minus r squared sine squared theta, or z is equal to 4 minus r squared, 1, for z just 4 minus r squared. But it says above xy plane, that's why we have z is bounded between 0 and 4 minus r squared. Very good. So let us do the computation. My triple integral, x squared is going to be r squared cosine squared theta, and my dv is r dz dr d theta. My z is bounded between 0 and 4 minus r squared. My r is bounded between 0 and 2. And my theta is bounded between 0 and 2 pi. So from that triple integral to this triple integral, that is going to be easier to compute. Very good. Let's take a look. Can I simplify this more? I get 0 to 2 pi, 0 to 2, and 0 to 4 minus r squared. I have r cubed cosine squared theta dz dr d theta. So first of all, your inner integral is with respect to z. It means that you can move this in front of your inner integral. this guy becomes integral 0 to 2 pi, integral 0 to 2, and here you have r cubed cosine squared theta, and here you have dz, which is now 4 minus r squared dr d theta. Very good. Can I separate these two integrals? Why not? I have fixed boundaries, and these two are separated from each other. Well, okay, I get integral 0 to 2 pi cosine squared theta d theta times integral 0 to 2. I have r cubed 4 minus r squared dr. Well, okay, the computation is not that difficult for you. You already know that this guy needs to be converted. And if you do the multiplication between these two quantities, you're going to have, let's see, a half times 2 pi times 16 minus 32 over 3, which is 16 pi over 3. We computed integrals of this form a lot. So you need to feel comfortable about computing the integral of cosine squared. And for this part, it's just a polynomial form. You're using the power function formula. For the spherical coordinate system, remember the definition. Rho is defined as square root of x squared plus y squared plus z squared. So rho squared is equal to x squared plus y squared plus z squared. What is this guy? This is just a solid sphere, right? This is a solid sphere. All values are included here. So since we know that the maximum radius is 1, rho is bounded between 0 and 1. If I slice this, the base is going to be just a disk. It means that my theta is bounded between 0 and 2 pi. What about phi? There is no restriction on phi. Phi is the angle between positive part of z-axis to the point. But by convention, we know that it stops at pi. So my phi is bounded between 0 and pi. There is no restriction here, absolutely none. So what about the triple integral? Your triple integral becomes the triple integral of e to power x squared plus y squared plus z squared, which is e to power x squared plus y squared plus z squared is equal to rho squared. So I'm just going to substitute that over here, e to power rho squared raised to 3/2 times dv. The important part for you is to make sure dv is written correctly. dv is rho squared sine phi. Well, d, for example, phi, d rho, d theta, and d phi. Now our job is to compute this. All right. You can simplify 2 and 2. You have all the boundaries in it. Rho is bounded between 0, 1. Theta is bounded between 0, 2 pi. And phi is bounded between 0 and pi. So this guy becomes the integral 0 to pi, 0 to 2 pi, 0 to 1, e to power rho to the third, rho squared, sine phi, d rho, d theta, d phi. Here I'm going to use u sub. U is equal to rho cubed, du is 3 rho squared, d rho. So this guy becomes a third integral 0 to pi, integral 0 to 2 pi, and the integral e to u du sine phi, and then here we have d theta d phi. Very good. So this guy becomes 1/3, and can we separate these? Why not? 1/3 integral 0 to pi sine phi d phi, integral 0 to 2 pi d theta, and here we have the integral of eu is going to be eu, but here u is rho cubed 0 to pi. So we get a third, and here we have negative cosine phi, 0 to pi, and here you have theta, 0 to 2 pi, and e to power 1 minus e to power 0. So if we simplify this guy, we're going to have 2/3 or another 2, so you get 4/3 of pi e minus 1. So that's how you compute your integral using spherical coordinates